minor variations. What you'll see that's rather interesting is so we have a big bounciness in these performance graphs, and the reason we have this is until you've got enough thread blocks to fully occupy all of the SMs on the GPU, you can end up in a situation where, so the performance here is faster than the performance for a slightly larger problem because this one happens to exactly evenly divide the work into the number of SMs. So every SM ended up with exactly the same number of thread blocks, which was perfect for completion time. If we have one more thread block than that, even one more, the effective performance for the whole thing goes down because we take a longer time to run because we have to wait for one SM to do the last thread block. And the rest of them are all sitting there idle. And so this is a trade-off we're making. If our goal was to do this range of problems over here, it might be a very, very bad idea to do multiple lattice points per thread because we're effectively increasing this padding size and we have fewer thread blocks to distribute to those SMs. So this is the kind of trade-off we're making. If we're willing to focus our problem range on things that are a little bit larger, then we can do much larger amounts of this unrolling. We can use more registers, and for large size problems, these issues go away because you have enough work. The work involved in the last group of thread blocks that run is inconsequential compared to the entire size of the whole calculation. But for small problems, it's a big deal. So this is something to keep in mind when you're thinking about writing your own kernels. How much work do you have? What size thread blocks should you use? Latency hiding may not be like talking about these numbers of registers and how many thread blocks we launch. That trade-off, it may be more important to preserve what little concurrency you have if you have a very small problem. So you might have to have multiple kernels. So in this case, we can decide which kernel to run based on the size of the lattice that we want to compute. And we can get better performance by figuring out which kernel has the right shape to give us the best overall runtime. And the last thing I was going to show just very rapidly is that a lot of these CUDA kernels can be relatively easily adapted to OpenCL. So here's an example of a four-way unrolled kernel ported from CUDA to OpenCL. The inner loop of the code looks identical. The only thing that's different here are the math routine names, or native reciprocal square root is the same effective machine instruction as the CUDA R square root call. So it's very similar. The CUDA code looks like this. OpenCL code looks like this. Almost the same. And there are other differences too, but I just wanted to show you that. One thing that's interesting, though, as Jim pointed out, OpenCL guarantees correctness, but it does not guarantee performance. Even though on NVIDIA's hardware, these two kernels in OpenCL and CUDA, they're the same formulation. They're doing exactly the same thing. They're compiled the same way, and they run at almost exactly the same performance. If I run that kernel on an AMD GPU or on an Intel CPU in OpenCL, they don't perform anywhere near the peak performance of the hardware. And one of the reasons for that is that the AMD OpenCL implementation for CPUs uses SSE, and Intel and AMD CPUs can only work on 4-element vectors at a time. And because of the way the hardware works, the compiler is not able to do the same sort of assignment of work items to SIMD lanes like it can in a warp on a GPU. And so the way you get it to use all 4 of those vector elements is to use float-4 types. And so instead of, if we look at this unrolled implementation here, we could do the same thing using a 4-element vector rather than a bunch of independent scalars. And in the OpenCL implementation, we basically compute a different, so we have a 4-element vector of offsets that we compute for a bunch of these lattice points. And this looks like a single, it appears very similarly to the original single lattice point per thread CUDA implementation, except that we're working with a float-4 type. So all the things that I've marked in green are 4-element vectors rather than scalars. OpenCL allows you to do arithmetic. They define operators between scalars and vectors, and so you can write this code very compactly. So this native reciprocal square root is also going to work on these 4-element vectors and so on. And so doing this, I'm basically computing 4 of these at a time. The register use is basically the same as for the other kernel. It's just written in a different way. But this is the way it has to be written in order to get peak performance on an x86 CPU or on the AMD GPUs. The AMD GPUs also use 4-element vectors in the hardware. And so that's something to be aware of. So even though OpenCL will let you run, if you want it to run fast, you may have to change things, and use things like float4 types. And I should also mention that those float4 types are not harmful on the NVIDIA GPUs. So I've done some experiments comparing a kernel like this versus the previous kernels, and they're roughly the same in performance in most cases. There are a few exceptions. But that means that you can, if you're very careful, you can probably design a kernel that uses 4-element vectors that runs pretty well, maybe not at peak performance, but pretty well, on all 3 of the major platforms, so on the AMD and NVIDIA GPUs and on the host CPU. So if you were using OpenCL, this is probably a major consideration though. And I think that's it. So and then I'll let Dave pick up from there. Does anybody have any questions? Yeah.
I'm wondering if y'all done any work, or there's been any work done on long-range forces for periodic systems, like an Ewald sum or a...
David will talk, hopefully we'll talk all about that. Anything else?
So some of the codes you listed, there's the DCS, different versions of the DCS.
And I have other versions, so the ones I gave you in the example code are the fast ones, but if you want the slow ones, I'm happy to give you those too.
All right.
Also,
Yes. Yeah. Thank you. Don't lose it.